Chapter 5, the second category, arithmetic and logic instructions. Today we are starting chapter 6 and it is on control and program control instructions. Okay? So what is in this one? In this one we will see those instructions which take the program up and down in the sequence. That's why we call them control. That means instead of going line number 1, 2, 3, 4, 5, 6, 7 in the microprocessor, sometimes we say from instruction number 3 jump to 15. And then we say from jump instruction number 18 jump to 2 back. Right? We call functions. These are all control instructions. So we will start first one, jump, which you have seen before, but now we will do like in the category, in detail. So what is the jump saying? The jump says go from one instruction and skip another of instructions and go to the target. But now what happens when there is a jump? Remember, every instruction has an address, right? In the memory, wherever the instructions are stored, every instruction has an address. So obviously when we will be jumping, the address will be changing, right? So instead of the address of the instruction number 2, maybe we are jumping to 13, so which will be the different address. So in jump, IP will always change. Whenever we will jump, instruction pointer contents will change because the address of the instruction is different. Sometimes also code segment address will change. That means the base address will change. When I am jumping in the same program, obviously it will have the same, it will be the same segment, right? So the base address does not change. But if I am jumping to another instruction in another segment, then the base address will change. So for example, I am saying I am jumping to a function and my function is stored in another segment. Then obviously not only IP will change but CS will change because CS contains the base address of the new segment and IP contains the address of the offset address of the instruction, right? So that's why we sometimes we have IP and CS both. Now there are two types of jumps. One is this one which we just saw as a jump, and this is the conditional. There are two types of jumps. One is the unconditional jump. The other one is a conditional jump. Unconditional means when we will say jump, it will not calculate anything. Microprocessor will not calculate anything, directly jump to the instruction. Like we say, call the function, right? When we say call function, microprocessor does not calculate anything. You just jump, right? But sometimes there are instructions in C programming, if you remember, if. This means now the microprocessor will calculate something because we said if and else, right? So if else it will be conditional, calling a function will be unconditional. So there are two types, unconditional, which means jump will always take place. But there is a conditional jump where microprocessor first will calculate the condition. See, it is the true or false. If it is true, jump. If it is false, do not jump. So that's why we have two types of jumps. Let's see the first one. The one which I am saying here, this is unconditional, JMP, which maybe you have seen in the previous lectures. JMP, jump instruction. This is unconditional. Always jump takes place. Since there is no calculation, there is no effect on the flags, because it will always just go to that instruction, to that address. But now, how big is the jump? How big is possible, right? Now it depends on which mode we are. Are we in the real mode? Are we in the protected mode? Or we are in the flight mode? In the original 8086 microprocessor, jump was very limited. Only 256 instructions up or down. From here, if my position is here, I can maximum jump will be 256 locations above. So 128 plus and 128 minus. So we used to call it label as a short. So it was total 256 from minus to plus including 0. But then we started seeing in the whole segment, that means jump will not be only 256 addresses, but the whole segment, which is 64K. Remember, each segment is how big? 64K. Code segment is 64K. That means jump can be in the full segment from bottom to the top. So this will be near jump. Okay? If the jump is beyond 64K, that means we are leaving the segment now, because full segment is 64K, right? If the jump is bigger than 64K location, so this means I'm leaving the segment, I'm going to somewhere else. Another segment, then we say here far. Now remember, we used to see near and far when we were writing procedures. Okay? So sometimes we will see short, which is for the old microprocessors. But these are the ones which are common in the new processor. Near means jump is in the real mode in the whole segment, 64K. And far means outside the segment. So that's why you see here. If it is a short and near, this means it is in the same segment, right? That's why you see here only IP will be affected. When it is far, it is beyond 64K, this means we will be leaving the segment, right? That's why you see here CS and IP are changing. Okay? Now you know the word internet, right? Do you know the word intranet? Some of you might have heard it. Intranet or intra-university, inter-university. Intra means within, inter means across. So if I say intra UAE university competition, that means inside the UAE university. When I say inter university, that means this university competing with the other university. Two different, right? So intra means obviously, that's why you see here intra segment, that means within the segment. Inter segment means now from one segment to the other. That's why we have internet means this network and the other network, right? Intranet means inside the university. Okay? Let's see examples of this one. Okay, we covered just this one. Let's see here. So what is it now? Let's see the example of a jump. There is a jump here, right? Instruction. So we start here. First, second, third, microprocessor just going in the sequence, right? Increment, then it says jump. Where it will go? And where is here? This offset, 106, right? So the next will be from here. This is called now the control of the program. That's what this chapter is about. Okay? So this is JMP only unconditional, because there is no calculation when we say jump here.
How we do it again?
Jump we said is unconditional. That means there is no calculation. So whenever microprocessor continues the sequence, it sees the jump, it will not calculate anything. But where to go? Label is here. So where is here in the address? Which is the 200 is the same. This is the offset. So next will be there.
So that will not end. But it will go.
No, I'm not talking about practical where it is going. I'm just showing you what does the jump mean here. Okay? In this case it is infinite, right? Okay. Now let's go. I told you 3, right? There are 3 sizes of the jumps. Short, near, far. Short, I said total 256, right? Locations, which means 8 bits, 2 to the power 8, which is a byte. Near means I said the full segment, 64K. And 2 to the power 16 gives you 64K. So near will be, label will be word. Short will be byte. Far means more than 16 bits. So here is the example now. If you see the instruction where displacement is only a byte, we will call it short. If the displacement is 16 bits, 2 bytes, this is a near jump. If the displacement is 32 bits, more than 16, then it is far jump. So byte, which is in the old microprocessors, right? Near, we always do near, right? Typically, jump within the segment. And far means we can jump outside the segment. Okay, let's see now the rules. Please. Let's see. Yeah.
The nearest 65, right? Less than 60. 16.
يعني تمشي في الكون.
Okay, so the first point is the size of the memory, right? How much it can go. Short is 256 locations, right? So if I say 256 addresses, which will be 2 to the power 8. So 8 bit, which means a byte. Displacement will be the byte. Okay? If I am saying near, this means 64K locations, which is the size of the segment. More than 8 bits. So if you see more than 8 bits and within 64K, so this means from byte to word, then it is near. If the size of the displacement is more than 16 bits, then it is far. So there are 3 sizes, right? Let's see now short and near. See the principle now. Where is my current instruction? JMP and displacement is 4, which is only byte. So this is in short jump. See here, JMP, after JMP, 2 bytes. So this is near jump. Okay? Now where it is jumping, see the rule. Remember in the previous lecture, somewhere I think maybe 2 weeks ago, where we said, whenever just microprocessor reads the instruction, IP will point to the next instruction, right? So just by reading JMP, where is the next instruction now? At 2, empty, because 04 is with this one. So this is my IP now. So the where it is jumping now, 2 plus the displacement. 2 plus 4 is? So you see where it is going. 6. Because this is not the address, this is the displacement. How big is the displacement? If it is a byte, so 2 plus 4 is 6. Come back here. Next example. By reading JMP, microprocessor will point to 3 because 0002 is the displacement, 16 bits. So 3 plus 2 is,
5.
this is where it is jumping. This is 5. Is it clear now?
Yes.
Any questions? Shall I go to the next one? Which is the for jump? Because we saw the short, we saw the near. Now let's go to the for. For means that means our jump is more than 16 bits displacement, right? Now jump and you see one byte, another byte, another byte, another byte, 32 bits. More than 16 bits, right? So this is a for jump. Now what are these values? Before we were saying this is IP, this is 16-bit IP, right? But when I say here for, you see here IP and this is, both values are given, IP, CS are given. Calculate the physical address from here. So in this example, okay, this is IP, okay, and this is CS. See here, first opcode, then IP, then CS. Opcode, IP, CS. What is CS? A300. So A300 shifts by 0, right? And what is IP? 0127. If you add what you get? A312. This is where it is going. A3127. So see now how microprocessor jumping depending on what is the displacement. If the displacement is a byte, simply just add the displacement with the current IP and jump there. Same thing with near, but the only thing displacement will be 16 bits. But with for, everything is available. Now, let's continue. Now, what kind of a jump is this one? Short, near or far? Remember the rule. If the displacement is byte, short. If it is more than a byte, within 16 bits, near. If the displacement is more than 16 bits, far. Near, because you see here it's more than a byte. Okay, so this is near. What is this one? Near, because the offset is in BX and BX is a 16 bit. Okay. What is this one? Again, by default is a word. So this will be 60, near, right? By for, either I put label or I provide 32 bit, right? So this is for. Look at these examples now. Tell me whether these are short, near or far. Example 6-1 from the textbook. See the instructions, you only just look at where the jump is, right? Explosive bar, move, aid, jump. And it goes to the next. Where is next? This one. What is the address here? 7. EB17 is the code of jump. Address is 7. So we are jumping from 7 to 20. 20 minus 7. What is this one?
20 minus 7.
This is hex, right? 16 minus 7. 9. 19 in hex. Anyone can tell me what is the decimal value? 19 hex. This is a byte, right? So this means that's why they wrote it here short, because we are jumping from 7 to 20. It's a short jump, right? Okay, how about example 6-2? Where we are jumping next to, where is jump? Next, which is 202. So from 7 to 202. 202. 7.
200. From 7 to 200.
Jump is from 7 and next is 200, right? So this one is 0. Will it be word, byte or 32-bit?
1 F9.
1.
F9.
So is it byte, word or double word?
W.
Is this double word? This is 3. So this is 888, 24 bits. No, this is a byte, 444, right? 12 bits. This is 12 bits. So it's more than a byte or less than 16 bit, right? So this is near. So this is a near jump here. Okay? Let's go to this one. Jump. Next. Where is next? To 200. From 5 to 200. Near, because it will be again more than a byte but less than 16 bit, right? So this is near. So this is how we see the jumps, right? Whether they are short, near or far. Small, within the same segment or outside the same segment, right? This was the meaning. So whether, I said again now, continue it here, whether it is unconditional or conditional, jumps are short, near or far. Doesn't matter whether it is unconditional or conditional. This instruction now is the conditional. Like if else statement, while statement, right? For loop where you put the condition, right? J is for jump, CC is for condition. So instruction will be J is something. What type of a condition, depending on the condition. Since there is a condition, calculation will be done, that's why the flex will be affected. But in unconditional, there is no effect because there is no calculation. Examples now. JA, if it is above, like greater, right? Jump below, less than. Jump on carry, equal. Okay, jump on overflow, jump on parity, jump on zero, jump on sign. So there are a lot of jump instructions to be learned, but depending on which jump you want to make, what you are going to check, which condition. So above is the condition, right? Below, carry. If the previous answer has a value above certain compared to something, right? Below compared to something. If there is a carry from the previous instruction, if the two answers were equal, if there is an overflow from the previous instruction, if there is a parity in the previous instruction, if the previous answer has 0, if the previous answer is negative. Okay, so let's see now and try to understand some instructions. Now what is this one? Compare AX and BX. What compare does? Subtract. And then what we are looking at when we compare? What is the answer, right? To decide if I'm comparing two values, then I decide, right? So what happens when we compare? Flags are checked. Okay? So when we say flags are checked, equal, which will be the flag for equal? Go back here. What is the, this comes from practice. For equal, 0 flag. So in the comparison, if the 0 flag becomes 1, this means true. Please, everybody is thinking about the quiz. I gave compare and someone was asking, it's a so small question, right? But nobody looked in detail. Equal. Equal means calculate the zero flag, right? Then it will be true. If the zero flag is 0, this means condition is not true. Don't jump. So this is what it means here. If after this instruction zero flag is 1, then it is true, we go to equal. If not, we continue it. This is what it means here. Okay, so see here how the condition is done. Same thing you used to do. If this one is equal to this one, do this one, else do that one. So if this is a true, we jump to equal. If it is not true, we continue it. This is what it means. Another example. What this one is doing. AND operation AL with 04. Now AND operation, what AND operation does? You know the AND operation, right? AL is a byte. Okay? 04 is so this everything is 0 except this is X, right? Okay? Now it says if not 0, this means if this becomes 1, not 0, right? Then we go to bit to 1. If not, you continue here. What?
How you know?
Just, is it not clear? Say it. It's not clear. You said what?
Why you say not, how you know it is?
Because then it depends, because my answer will be what is the value in the A, right?
Yeah.
Then either this will be 0 or 1, right? If this becomes 0, so this means it is false, right? Then I continue here. If this remains 1, which means your answer is not 0, right? Which means then I will be jumping to bit to 1, right? Everybody is still in the quiz. Not right. How about this one? Try to understand this one. How about this one? What is this one? Move 3 to CL, right? Please. So CL is 3. Shift right AL by CL. So AL is this one. Okay? This is AL. And this is carry. When I'm shifting it, like we learned in the previous lecture. I will be shifting this one 3 times. This whatever is here, this one will come, then this one will come, then this one will come, right? Whatever is the final carry. Now it says, if there is a carry, see here, if there is a carry. So this means when I finish this one, in the carry, if it is a 1, then it is true, right? Then I jump to bit to 1. Otherwise, this is how we use the jump instruction in assembly. That's why I see here, if then else. What is happening here? Can you read the program and understand it? What is happening here? Leave it. Okay, I will give you the result next Sunday, right? What is this one? It says move some value into AX, right? Then that value goes to, which means what did we do? We defined the base address, right? DS has the base address. In SI, I am putting the source address. In DI, I am putting the destination address. And counter, I am saying it block size. Now here comes the loop. Okay? And the loop, what I am doing? I am going to this memory and SI has the source address, right? I am reading a byte. Move from this memory to register AH, which means I am reading a byte from this memory and I am putting it into AH. And then from this AH I am putting into another memory, which is the destination. Okay? So this means I am reading from source a byte and placing it into memory a byte. And then I am incrementing the address. One, I am incrementing the other address. So first I place from here to here, then I went to the next address, right? Then I will, so this I am increasing the addresses, decrementing the counter. If the counter is not 0, go to next. Because I am decrementing the counter, right? Once it will be 0, I am out of the loop. Okay? Any questions here? This size of programs you will be writing in this chapter only. After this chapter, assembly is finished. Okay? So the purpose of this chapter is knowing the control instructions like jump. So far we are doing the jump, right? Then in the next lectures we will do the writing functions. Okay? So we stop here.